Welcome to this video in the rates 2 topic on calculating rate constants from reaction half-lives. Now, highlight for this is only for first order reactions. So once we're satisfied that our reaction's first order, and the hallmark of that is that we have a constant half-life here, in this case it's 14 seconds. Once we're sure we've got a constant half-life, if you're not sure how to determine half-lives, then watch the previous couple of videos. Then once we're sure we've got a constant half-life, then we've got a first order reaction, and so we can think about how we could calculate what the rate constant is from that half-life. Now let's just consider a few reactions here. So in purple first, I've got a reaction with a rate constant of 0.02, and that's what the concentration time plot looks like. You can see it's a very, very slow decay. And if we work out the half-life for this reaction, we find it's around about 35 seconds. 35. Okay, now let's think about this blue reaction here. So I've used instead a K value of 0.05 in this case. We've got a reaction which we would call faster. Obviously it's going to be slower towards the end, but initially at least it's going to decay more quickly. So that's what the rate constant does. And if we find the half-life there, it's around about 14 there. So that was 14. And then if we go for the green reaction there, which we've gone up to 0.1, then the half-life there is about 7 seconds there. So if we just think about this relationship here, then what we've got here is, so to go from say the blue to the green line, is we've got a doubling of K, but we've got a halving of the half-life. So we've doubled the rate constant, we've halved the half-life. And let's just see if that type of relationship exists again, and just use a different colour pen this time to show it. So here we've multiplied the rate constant by 5, and sure enough, to go from there to there, we've multiplied it by a fifth, or we've divided by 5. And so what we've got here is an example of inverse proportion. So we've got the rate constant here is inversely proportional to T1/2. And the proportionality constant, it turns out, is actually, so I just show you that should be a lowercase k to distinguish from the equilibrium constant, is actually the natural logarithm of 2. So you should have a button called ln on your calculator, log to the base e of 2 divided by T1/2, and that is the formula that governs the link between the rate constant and the half-life. And just remember that we could be given, in this case, we could be given the half-life and have to work out the rate constant. In some cases we might be given the rate constant and asked to work out the half-life. So pause the video and see if you can rearrange that formula. You should have got the following. You should have had T1/2 equals ln 2 over k. So I would remember it in this format, but you could be asked to use it in this one.